Hello everyone, and welcome to Gem Academy. This is really a very important lesson in which we are going to talk about one of the most important theorems that you will encounter in this course and in introductory physics in general, the work kinetic energy theorem. Now, this theorem is so important because it not only simplifies the calculations, it also makes the calculations straightforward. Now we know for sure that work is the transfer of energy when a force moves its point of application. In other words, whenever work is done, energy is transferred into or out of a system. Now when energy is transferred into a system, the work done is positive. But when energy is transferred out of a system, the work done is negative. Let me put it another way. When work is done by an external object on a system, it transfers energy to that system, in which case the work done is positive. But when a system does work on the surrounding, energy is transferred from the system to the surrounding, and the work done is negative. Now, we also understand that Newton's second law states that the net force acting on an object is equal to the mass of that object multiplied by its acceleration. So the work kinetic energy theorem is simply a theorem that shows us the net effect of doing work on a system. Remember, that shows us the net effect of doing work on a system. In just the same manner as Newton's second law tells us about the net effect on a system, when you apply a net force, what happens? The momentum changes. And Newton's second law states that the change in momentum is equal, the rate at which the momentum changes is equal to the net force acting on the system. So let's keep it going. Suppose we have a box. A box is being pushed by an external force F to the right, and let's say that the box initially has speed Vi, and because of the application of the force, the box moves to a new the box accelerates to a new speed Vf. We know that the initial kinetic energy Ke initial is simply equal to 1/2 mv initial squared, and the final kinetic energy Ke final is equal to 1/2 mv squared final. So when the application of a force causes the velocity of the box to change from Vi to Vf. In other words, the speed of the box changes since it's moving along a straight line. Now the change in kinetic energy, delta K, will be equal to 1/2 mvf squared minus 1/2 mvi squared. This is equivalent to 1/2 m bracket v f squared minus vi squared. But if you recall very well, vf squared is equal to vi squared plus 2a delta x, where delta x is the displacement of the particle from the initial position to the final position. This essentially implies that that a delta x will be equal to 1/2 bracket vf squared minus vi squared. Now, what do you notice? We can essentially substitute this back into that expression. If we do that, you will notice immediately that the change in the kinetic energy, is equal to m multiplied by a delta x. This is equal to MA multiplied by delta X. Now, what is MA? MA is the net force acting on the object in accordance with Newton's second law of motion. So MA is simply the net force acting on the object in accordance with Newton's second law of motion. So this essentially means that the change in the kinetic energy will be equal to the net force multiplied by the distance or the displacement covered. Now this is a pretty important equation. By definition, the net work done by an object on a system is equal to the net force multiplied by the distance covered by the system. In other words, we're essentially saying that the change in the kinetic energy will be equal to the net work done on the system. It's essentially equal to the net work done on the system. Isn't this powerful? This is a very, very important result that tells us that the net work done on the system is equal to the change in the kinetic energy of the system. In other words, the work kinetic energy theorem tells us the net effect of work done on a given system. When work is done on a system, the kinetic energy of that system is bound to change. Let me say that again. The net work done on a system is equal to the change in the kinetic energy of that system. So this implies that W net will be equal to the kinetic energy final minus the kinetic energy initial. This, my friends, represents the work kinetic energy theorem. Represents the work kinetic energy theorem. Now here's the deal. This is important, and I'd like for you to pay attention. One, if the net work done on the system is zero, then the change in the kinetic energy of the system is going to be equal to zero. This simply means that the initial kinetic energy is equal to the final kinetic energy. In other words, the initial velocity is equal to the final velocity. When the net work done on the system is zero, the kinetic energy does not change. To put it in a simple word, the velocity or the speed in a particular direction remains the same. Keep that in mind. When the net work done on a system is zero, the speed of that system doesn't change. The speed of that system doesn't change, even though the velocity may change. A typical example is an object moving on a circular track. The speed stays the same, the velocity changes, and the reason the speed remains the same is simply because the net work done on that object is zero. Now the next thing that I would like for you to notice too, if the net work done on the object is greater than or equal to zero, this would mean that the change in the kinetic energy is greater than or equal to zero, and this would mean that the V final is greater than or equal to V initial. What does this imply? It means that when the work done on a system is positive, let me say that again, when the net work done on a system is positive, the speed of that system increases. The speed of that system increases. In other words, an increase in the speed of a system is an indication that an external agent is doing work on that system. Why do I say so? Because when an external agent does work on a system, the work done is positive, which means that when the speed increases, 1, the work done on the system is positive, and 2, something outside of the system is adding energy onto the system. Now the third point I want to make is, if the net work done is less than or equal to 0, this means that the change in kinetic energy is less than or equal to 0, which means that V final is less than or equal to V initial. What does this all mean? It means that when the net work done on a system is negative, the speed of the system decreases. Remember that work done is negative when work is done by the system on the surroundings. Let me say that again. When work is done by the system on the surroundings. When the system does work, it transfers energy to its surrounding. And when that happens, the speed of the system decreases. The speed of the system decreases. So a decrease in speed is an indication that the system is doing work, thereby dissipating some of its energy to the surrounding. A good example is work done by friction. Work done by friction. Now, before we close on to today, I just want to re-derive the work kinetic energy theorem in a much more general term. Remember, we have a box of mass m. We have a box of mass m being pushed to the right by a net force F. So the net work done on that object, W net, by definition, is equal to the integral from xi to xf, F net multiplied by dx. Now, by definition, F net is equal to m multiplied by a, which is equal to m dv over dt. Also, by definition, it is important for you to keep in mind that a, which is dv over dt, is equal to dv over dx multiplied by dx over dt. This is gonna be equal to v dv all divided by dx. That is another way of expressing the acceleration of the system. And if that is true, this would mean that the net work done will be equal to the integral of F, which is just going to be m, multiplied by a, which will be multiplied by a, which will be v dv over dx multiplied by dx. The beauty of this equation is that the dx will cancel, and this will be equal to the integral of mv dv, and we're integrating from v initial to v final. This would imply that W net is going to be equal to m v squared over 2 from v initial to v final, which means that W net is equal to 1/2 mv final squared minus 1/2 mv initial squared. This gives us, in a much more general way, the work kinetic energy theorem. The work kinetic energy theorem. Now, In the next series of lessons, I'm going to do some really important examples that will emphasize the importance of this theorem and will also guide you as to how to use this theorem to analyze some very complex and interesting problems in physics. Now, I know that you may have questions or comments, the things that you may like or not like about this lesson. We will appreciate it if you put it in the discussion forum below this video. Thank you so much and remain blessed. Bye-bye.